Welcome to the fourth lecture video in our Class 16 series of lecture videos. And so as we saw in the third video, conformations could play a critical role in reactivity for the bimolecular elimination, the E2 mechanism. So let's look at another example with something for which we're fairly familiar in terms of conformational analysis. Let's look at this particular cyclohexane ring, which has a 1,4 substitution pattern with bromine and an isopropyl group. If we subjected that to sodium methoxide and methanol, we're going to do an E2 reaction. Our secondary carbon is a little too slow to wait around and do SN1, and it's a little too hindered being on a not only secondary, but on a cyclohexane ring to do SN2. Our nucleophile is a good, relatively strong base, so we're going to do E2. And so what we would produce, or what we would get out of this, is a racemic mixture of alkenes. We'd have this one alkene where our stereocenters are, and because it's racemic, that means we have an equal amount of the non-superimposable mirror image where the stereocenter is S. Versus instead of having our 1,4 cis substitution for our bromine and isopropyl group, what if we had a trans substitution and we exposed this to the same reaction conditions of sodium methoxide, methanol? We'd want to see an E2 product, but wow, no reaction happens, or a very slow reaction happens. So why is this substrate giving us so much trouble compared to the cis-substituted cyclohexane substrate? Well, let's look at the cis-substituted cyclohexane substrate. In its most stable conformation, the isopropyl group is equatorial and the bromine is axial. Well, it just so happens that if the bromine is axial, on the beta carbons adjacent to it, we have hydrogens that are anti in the same plane as our bromine group, and that's what we need for the E2 reaction. So if our methoxide, let's take this methoxide and it plucks off this H that's labeled B on our cyclohexane ring. And we give our electrons there to form a double bond between this carbon-carbon bond in the cyclohexane ring, and we kick out bromide. Well, then we end up with this particular alkene, which, if we flipped it over on its back, would give us the S stereocenter. And I did not draw the complete arrow pushing mechanism for the alternative proton that's anti-paraplanar on a beta carbon, that is a carbon adjacent to the alpha carbon, which bears the leaving group. But if our methoxide plucked off HF and we formed an alkene between this beta carbon and this alpha carbon, we'd get this particular cyclohexene ring, which would be the R stereocenter. So of course, methoxide doesn't know, there's no energetic difference between plucking off HB or HF, and so we get, an equal amount of these two enantiomeric cyclohexenes, and so we end up with a racemic mixture. So the full arrow pushing mechanism shown for HB, you could write a full mechanism for HF if you wanted to, plucking it off. I think this also gets to the point of, being able to remember how to convert certain substitution patterns in bond line to chair conformation. So obviously the bromine and the isopropyl group are on the same side of the ring formed by the, cyclohexane. And so we'll go ahead and show you, here we've got a cyclohexane model. I've put the bromine and the isopropyl group on the same side of the plane formed by the ring. So if we flatten this ring out, yes, indeed, the bromine and that isopropyl group are on the same side of the plane formed by the ring. So if we put it back in the chair conformation, our isopropyl group is equatorial, our bromine is axial. In the notes, we had it drawn this way. And you can see that this is our alpha carbon, where our bromine is, bonded. It's the leaving group. This hydrogen is anti-paraplanar to that bromine leaving group, right? You can see that through that Newman projection. This other beta carbon has a hydrogen that is also anti-paraplanar to the bromine. We'd have to flip the molecule around to put it in that Newman projection position where you can see, oh, that hydrogen is anti-paraplanar to the bromine. So depending, this is our most stable conformation of our cis-substituted bromine isopropyl, in a 1,4 substitution pattern on our cyclohexane ring. Why? Because, putting the bromine in this position is plus 0.55 kcals per mole, whereas putting the isopropyl group in an axial position would be plus 2.20 kcals per mole. So this is the more stable conformation. Now, of course, we have to consider the alternative case. So the trans substituted, we'll go ahead and do that. When our isopropyl group has a trans substitution compared to the bromine, our most stable conformation has both the bromine and the isopropyl group in equatorial positions, right? This would be the least stable conformation by, 2.2 plus 0.55 kcals per mole, so 2.75 kcals per mole. This would definitely not like to get into this conformation. That would add to the activation energy in order to do the E2 mechanism, because it's only this conformation where we have the bromine axial that we have anti-paraplanar hydrogens, Hc and He, on the adjacent beta carbons that we could pluck off to form, our bimolecular elimination alkene products. So in the most stable conformation, there are no hydrogen atoms on the beta carbon that are anti-paraplanar to bromine. In the least stable conformation, however, both Hc and He are anti-paraplanar. And the E2 reaction is now possible, but that conformation is high in energy. It has a high activation energy, so it would be slow, and it would not want to go. So you could prove to yourself that neither HF nor He is anti-paraplanar to this bromine by drawing a Newman projection for this most stable conformation. So hopefully you have a better sense of how the E2 reaction might concern these interestingly substituted chair cyclohexane molecules. And that completes this particular lecture video. I'll see you for the next one.